Good afternoon. Thanks for coming here to our final presentation of the series. Um, my name's Tim White. I'm a research professor in the Earth and Environmental Systems Institute and the Department of Geosciences. I did my graduate degrees here in geosciences and then did a postdoc at the University of Iowa, worked for the USGS, US Geological Survey for 4 years, and then I've been at Penn State full-time since 2003. I am going to introduce Nick, but before I do, I'm going to talk a little. And we are going to present to you this talk entitled Diagnosing a Potential Critical Mineral Deposit in the Coal Regions of Central PA. And I want to give you some context. Before I do, I want to make some acknowledgments. First, this work has been ongoing for at least 5 or 6 years. We have to acknowledge our dean's support of this through his Critical Minerals Fund and financial and logistical and collaborative support from the college's Center for Critical Minerals, in particular Sarma Pisapati and Barbara Arnold, who I've worked pretty closely with over the years. We've had close collaborations with the Pennsylvania Geological Survey, specifically John Newbaum and Rosanna Baer. We've had a series, I'm not going to list each of them, of geosciences senior theses. And one of them in particular, the last one, Michael Coball, is ongoing, and we'll report on that soon and allude to it a little today. Maureen Feineman from Geosciences has been a close collaborator, including with field work and oversight of Nick, the 2020 senior thesis, and more recently in helping us to characterize the clays and claystones we're going to talk to you about today. Alan Larson and George Kaufer, both Northern Center County coal people, one an engineer now, the other a coal company owner and coal miner. And then finally, David Russ. David Russ, so if you've looked at our website for the Earth Talks this semester, you'll see Tim White, me, and David Russ listed as the organizers. And it's really an injustice to David. I have played a minor role in this. David is a graduate alum of the department. He's an emeritus scientist and leader from the US Geological Survey. He's also, until recently, been on our Geosciences Department Alumni Advisory Board, and he continues to play a crucial leadership role in that group's critical minerals working group. And so Dave deserves a hearty applause, not just from me, but all of us. So I'm going to do that right now. Thank you, David. I know you're on there. Thanks for what you've done. Okay. So today we're going to switch gears a little, and we're going to talk about the geology of lithium deposits. And specifically, we're going to focus on what I've highlighted down there below, sedimentary deposits, specifically within clays and clay stones. Before I get into that, I do want to mention and acknowledge there are sources, and I should say we're going to focus on lithium today. We'll talk a little bit about rare earth elements, but we're going to focus on lithium. There are many other sources of lithium, and in fact, those first two really are better established historically as sources of lithium to the global economy. The pegmatites, these coarse-grained granitics, were presented to us in an earlier seminar by Jesse Rymick from our department. And good examples of those are the existing mines and prospects in the mountains of North Carolina, and some of the historical and maybe future mines in Maine. Continental brines are the source of much of the lithium that makes its way into the global economy. These most often form high The best examples are in the Andes, in playa lakes that derive lithium from volcanic sources and then are concentrated through evaporation, including into salts. And then finally are these clay-hosted deposits that we're going to focus on. You know, probably the best example today in the United States is Thacker Pass, if you've heard of that, the volcanic clay stones, volcanic lacustrine clay stones in Nevada. We're going to focus on clays and clay stones in the coal basins of Pennsylvania. And while we have worked out here in the anthracites, we're going to be talking about sites from up here in the north central fields and down along the Allegheny front in the main bituminous field. And before I launch into this and introduce Nick, I want to acknowledge that much of the wealth, not only of this state, but of this nation, has been derived from the extraction of coals in Pennsylvania and really through the entirety of the Appalachian Basin. And so the quality of life and that our society has achieved is in no small part due to our recognition and extraction and combustion of these materials. Now, having said that, there is a legacy of that extraction that includes, in our state alone, up to 250,000 acres of abandoned mine land, unreclaimed from historical strip mining. There are up to 820 abandoned coal refuse piles, reaching up to some estimates 2 billion cubic yards of material covering 8,500 acres. We have over 90 coal ash dumps associated with power plants burning the coal, and we have thousands of acid mine drainage seeps impacting over 5,000 miles of our streams that are either totally dead or at least impaired to some serious extent. Now, the reason I say that is that first headline in the Times is from last March. The announcement on the right is from this month. But the point here is that the federal government, particularly the Department of Energy, is pointing a lot of resources to looking at the coal measures and in particular all those wastes associated with past and ongoing use of the coal resources. And arguably, we've wasted a lot of material in the process of extracting and using them. So I want to just turn back briefly to a topic that Maureen raised in her presentation, which was one called the honorable harvest that comes from the Haudenosaunee Nation. We would think of it as the Iroquois Confederacy. There's a whole bunch of things associated with that honorable harvest, but the ones I wanted to highlight for today are minimize harm and don't waste what you take. And I would argue that we've done both of those. And maybe now looking at all that waste is an opportunity for our society to kind of circle back and maybe address some of the harms of those wasteful activities. Okay, so in addition to that, really what I want you to focus on this slide is the generalized stratigraphy on the right. And don't worry about the details, but just know that when I wave my hands and show you that map of Pennsylvania where their coal is, there's on the order of 40 individual coal seams within that space. And what Nick is going to show you is that at least our cursory look at these resources would indicate that rare earths, lithium, are concentrated in specific horizons, most particularly, and I don't want to steal too much of his story, but down here low. And so I'm bringing this up right now simply to state that as we move forward, whether we're thinking about actually mining material today to extract these resources, or how to get after these waste piles and ash piles and the acid mine drainage seeps, knowing that there are horizons that are richer in these various elements than others could help us develop a strategy of prioritizing. Well, let's go in and look at these mines, these waste piles, because they probably have more of those materials than others. Okay, this is not a new idea. The USGS recognized in the 1970s, and here you can see the citation, Turtelot and Brenner Turtelot from 1978. In that particular study, they were looking at lithium in claystones around the United States. And you'll see, if you look quickly, the highest value on that map up there on the upper left is here in Missouri. Turns out it's in age equivalent rocks to the ones we're looking at today. But beyond that, the highest values are up here in the Northern Appalachian Basin. And over here on the upper right, you can see an image from that original report. And if you don't recognize, this is the outline of Center County. Campus is sitting right about here where the red dot is. And so Clearfield County, Clinton County, and Northern Center County have the highest lithium values in the Northern Appalachian Basin, at least as reported by the survey in these 1970s report. So at least some of what we set out to address are questions like, is this real? Are these values, can we find them today and verify what they've seen? And I'll point out that they also notice that these high values decrease to the west and to the south. And so is that distribution something with more samples we can verify or not? If you look at these plots of lithium values at several given sites, you'll see that there's quite a range, right? There's stuff up to 2,000, greater than 2,000 parts per million, but most of the values are down here quite low. So to what might we attribute the range in these lithium values at a particular site? And then finally, can we predict the presence and distribution of high lithium values? Just to provide some context, here, up to 2,000 parts per million lithium in these Mercer claystones that we're going to focus on, compared to a table showing some average values for existing or lithium mines that are currently under development. And you can see here, Thacker Pass, same stuff, claystones, Jadar Basin, also claystones. We're not even close to the high values. But if you look at this range of values, the 2,100 parts per million starts to look like, well, maybe it's something worth thinking about. So just to provide you some context, I'm going to hand it over now to Nick. And before I do, and while I'm handing him the microphone, I'm going to tell you, Nick is a postdoc here in the Earth and Environmental Systems Institute, working with me. And he got his bachelor's degree you should come up here so I can hand this to you. He got his bachelor's degree at SUNY Geneseo, a master's degree working with Carl Brett at the University of Cincinnati, and a Ph.D. at the University of Wisconsin. And he's a busy guy. His wife is an academic in the Department of Education at Buffalo State. They have, I think, a 4-year-old son who I've met and is quite an active young fellow. And so I'm eager to listen to what Nick has to say, but also will state that I've enjoyed working with Nick, and I think we've learned a lot, and I hope that comes clear in this story.
Thanks, Tim. Yeah, so on that note, I'm going to start providing just a little bit more context for these samples, these high lithium samples that Tim just introduced here, some of the geologic and spatial context. Our study area is the Appalachian Basin. This is a northeast-southwest trending depositional province that covers a big swath of the eastern U.S. And it consists primarily of relatively of Paleozoic sedimentary rock, so 540 to 240 million years ago, situated in this depositional province. And um, this Appalachian Basin is what's called a foreland basin. And so repeated episodes of mountain building and uplift on the eastern margin of the continent creates mountain building that will weigh down the crust, creating sinking and subsidence in the basin, in the adjacent basin. And so this creates a deepening, but it can also, through the flexure of the crust, create parts where part of the crust will pop back up, called a forebulge. And so this basin topography is what we see across Pennsylvania on this line from Philadelphia to Scranton, all the way over from east to west. And this is like a side view, essentially. And this is where these rocks are forming that we're going to be studying today. Now the rocks themselves, what they look like, you see a lot of coal formed from terrestrial organic matter, tropical plant fossils, fine-grained claystone, channelized sandstones. And what all of these things are telling us is that the rocks where we're finding these high lithium samples are being deposited in warm, tropical, low-lying environments. Think rainforest, jungle, although it predates a lot of like animals, so it's like just amphibians and insects and things like that. But think very different from the modern Pennsylvania. From these rocks, from this geological evidence, scientists have reconstructed a general idea of what the environments are across this region, which I've superimposed over the modern map. And again, what it is are flat-lying floodplains, meandering streams, and occasionally, during times of high sea level, you're getting the incursions of these shallow seas into the Appalachian Basin that's reaching just about up to Center County, where we are today. So during the rocks themselves are deposited, that we're looking at, were deposited during a time called the Carboniferous period, about 359 to 299 million years ago. And at this time, the block of continent that's now North America was straddling the equator. And Pennsylvania itself is sitting just south of the equator. So again, think equatorial, low-lying, lots of sediment being washed off these mountains, meandering rivers, think something maybe like, Louisiana or something. This is the environmental context for where these rocks are forming. So, looking more specifically at the rocks themselves and the Carboniferous generally, the time period when these rocks were being formed, I've put up here a timeline of part of the Carboniferous, specifically the upper subdivision of the Carboniferous, which is called the Pennsylvanian. And there's several columns here with names on them, and these columns are the general rock layers that you find across these different regions, which are labeled up at the top here. And I want to draw your attention specifically to these rocks right here, specifically the lower one called the Pottsville, which was deposited early, like towards the early part of the Pennsylvanian, 315, 310 million years ago. And what's happening in the Carboniferous as these rocks are being deposited? It's a time of great global upheaval and dynamic change. Prior to the modern ice house, one of the previous great ice house events was during the Carboniferous. So you're getting this massive glaciation, sea level low stand toward the early part of the Pennsylvania, but that's starting to ease off. And as the Earth is warming, ice sheets are melting, sea level is starting to rise gradually, and you're starting to get the marine realm occasionally transgressing onto the continent. And as you're getting this transgression and onto the continent, this is when you're starting to get some of this first deposition in Pennsylvania. So we've got the blue line right here is the general sea level curve. The brown line is the general global temperature reconstructed from various proxies. But what you'll see is it's not a monotonic change from low sea level to high level. It's a dynamic back and forth, high, low, resulting it's this rapid high order sea level rise, sea level fall associated with these glaciation, deglaciation events. And what we see is that lithium, so what I plotted here is the lithium abundance, just bulk lithium abundance binned by the rock layers that the sample was found in. So each one of these dots here is a sample of a rock, and I've binned it by the rock layer that it comes in, whether it comes from this lower layer, like Pottsville and equivalents, Allegheny, or younger rocks. And what we started to notice is that there seems to be a distinct trend through time, where all the very highest lithium values seem to be clustered down towards the bottom of this rock column in the Pennsylvanian, with values up as high as 15 to 2,000, some of those high values that Tim was talking about. And so, first off, before diving too much into that, I want to talk about where all this data is coming from, and it comes from a variety of sources. Some of the early 70s USGS work done by Turtelot, some of the work that Tim and various faculty and staff and undergrads have done at Penn State. But the lion's share of the data comes from the Earth MRI initiative, this huge database with a lot of geochemical information that helps shed a lot of light on the study that we're doing here, and it's a really incredible resource that was really pivotal to helping understand some of these patterns that we're seeing across space and time. So we want to acknowledge that the effort of the USGS to make that available for us to use. So I talked a little bit about how the lithium values were distributed in the vertical rock layers, with clustering towards the bottom, declining upwards. But there are also interesting patterns that we see in the lithium values across space. So in this plot here, I've just plotted up the lithium values where each sample was taken. And I've color-coded them based on the lithium abundance here, with darker reds being higher lithium, lighter whites and pinks being lower lithium. And this is just a scatter shot of data points. But as I was plotting this up, I noticed there seemed to be several distinct hotspots that I've outlined qualitatively here, just to draw your eye to them. And what I noticed generally was that there's a trend towards increasing lithium as you get into central Pennsylvania, as Tim alluded to. So the highest, and what it shows is that the highest lithium in these geochemical data sets is from Pennsylvania. But why is that? Like, what about the environment, the time, the context, the geology could help explain that? And so to consider a few different options, first I want to dive in a little bit more detail with the stratigraphy. So this is, imagine like someone dug a ditch along this blue line that was several miles thick, and we're looking at the rocks in side view. That's what you would see right here. And the Pennsylvanian rocks are the flat-lying rocks up here, sitting on top of maybe gently dipping older units. And the Pottsville is this thin veneer that's sitting on top of that tilting stuff at the base of the Pennsylvanian. And as Tim mentioned, it's not within these Pennsylvanian units, there's a lot of finer order variability of coals, limestones, clay, sandstone. All of this is, and this is all reflecting that dynamic variability in sea level and climate that I was mentioning earlier. So this is like a very, very dynamic stratigraphy that we're working with lots of change vertically and spatially. But what we see in the rocks from Pennsylvania as well is that same pattern, where you're getting the highest lithium values in this thin Pottsville unit down here. Still somewhat elevated values in younger units, but declining upward. And specifically, the places where we're seeing a lot of these high lithium values are from this rock layer called the Mercer, which the Mercer is a clay, and its claim to fame, aside from lithium, is that historically it's been mined as a refractory clay. So it's a clay that makes a high temperature resistant ceramics that get used in kilns and stuff. And what's interesting is that the other elements don't show the same strong stratigraphic variability that we see in the lithium. So for example, I just plotted rare earth elements right here, also color-coded by lithium content. And there's not quite as strong a distinct stratigraphic pattern. So whatever's controlling the lithium abundance through this vertical stratigraphy seems to be restricted to the lithium, or mostly restricted to the lithium. So getting back, So what's controlling these patterns across space and in stratigraphy? So zooming in on this part of the northern Appalachian Basin where we're working, instead of looking at a bunch of little dots, this is what that same data set looks like as a heat map. And what this result revealed is that there seem to be two very distinct lithium hotspots in the northern Appalachian Basin, one centered on Clinton County and one centered on Clearfield County. And how do these hotspots fit in the context of the paleo environment and depositional setting? Here's that earlier environmental map that I showed, superimposed on this heat map. And interestingly, the lithium hotspots seem to be situated right on the margin of where this shallow seaway occasionally came in. So it's these from the geology itself, from the sites where these samples are taken from. The rocks are not marine, but they're sitting very, very close. They're this low-lying area that's probably occasionally flooded intermittently, or even like during high stand, like even when the sea level's high, these samples are probably along the coast somewhere, or like reasonably close to the coastal areas. Now, additionally, where these hotspots are located are on the forebulge that I mentioned earlier. So here's the cross section that I showed earlier. On the right, I've shown some modeling done on subsidence during the Pennsylvanian. And the places where you're seeing the highest lithium are places where there seems to have been almost no subsidence. So possibly aligning with the forebulge, this shallow bench that's sitting in the middle of the basin. And this is reflected in the overall stratigraphy of the Pottsville group across Pennsylvania. If you were to look at the Pottsville rocks from Scranton all the way over to Pittsburgh or something, what you notice is that on either side of the state, the rocks are quite thick, but they thin to this veneer in the middle of the state, right where the high lithium values are being found. So it seems that they're possibly perched up on this hotspot. So to kind of summarize everything, these rocks are sitting in a low-lying but somewhat perched up little bench within a basin. It's tropical, it's humid, and you're getting sediments being fed from all sides washed out of the mountains, and are forming these lithium-rich clays, possibly reasonably close to the coast within the Appalachian Basin. So this is not the type of environment that you would generally expect to be enriched in lithium. So how is lithium getting enriched in these local environments? What's the ultimate source of the lithium, and how does it get there? Looking again at the elemental geochemistry from the Earth MRI data, we can do sort of a multi-dimensional analysis of the relationships between how different elements are associated with each other, like when you find a certain elements enriched in the sample versus depleted. And what we see is a continuum from alkali-rich lithium-poor samples all the way up to lithium-rich alkali-poor samples that are instead enriched in very immobile lithophile elements, things like zircon and niobium and tantalum, that tend to be more locked into the grains that they're located in. So this seems to be indicative of a strong weathering trend from a possibly highly fractionated and felsic parent material. And this weathering intensity trend seems to be the predominant overall control on the overall chemistry of these samples. But again, still, where does the lithium itself seem to come from? We have two potential plausible ideas. The first is that could it come from a weathered pegmatite from, say, the Appalachian Mountains, getting weathered and bits of lithium-rich stuff is washing down. So what's a pegmatite? A pegmatite is an intrusive igneous rock that's highly fractionated, and it's highly as it's evolving, you get pockets of it that will be really, really enriched in things like lithium and cesium. And this is one of the major sources of lithium in the modern setting. So the question is this plausible? Is a nearby lithium pegmatite plausibly a source of lithium washing into the basin, getting incorporated into these Mercer clay stones. So going back and reorienting to our lithium heat map, I looked at the USGS geochronology database to see the distribution of intrusive igneous rocks in this area. And there's a lot of intrusive igneous activity. There's a lot of like plutonic, magma plumes coming in along the eastern seaboard. So pegmatites are plutonic rocks, so this is good. But also on top of that, there are several lithium, cesium, tantalum pegmatites identified across this region as well. So you're getting lots of igneous activity and some pegmatite emplacement reasonably close-ish to where the lithium hotspots are. And from what people have reconstructed from current information, like from like paleo currents, like reconstructing the paths of ancient rivers, it's plausible that Pottsville river systems, that during the Pottsville deposition, you're getting river systems delivering pegmatite material into the basin. But it's still kind of a long way to bring all these lithium minerals. So another possibility is that it's volcanic. So possibly the same, lithium-enriched magma sources, but instead of intruding as a pegmatite and then getting weathered and minerals washing into the basin, maybe some of that magma is erupted, and this lithium-rich ash is blowing into the basin. And this is consistent with some of the high lithium deposits that are being explored today. A lot of volcanic associated lithium deposits in like the Western U.S., for example. And also, here's two geologic columns showing the vertical stratigraphy. Don't worry about reading the names, but I've plotted, so this vertical axis is time or geology or stratigraphy. And where the Mercer is situated is right here. And each of these red stars right here are other claystone beds situated just below or just above or nearby the Mercer that have been interpreted as volcanically derived claystones. So the Mercer itself hasn't previously been identified as a volcanically derived claystone or a claystone incorporating volcanic material, but it's close to other ones so it seems plausible. And from these earlier studies, people have argued, have reconstructed the paths of ash blowing into the basin, and these studies, a lot of these other volcanic derived claystones are a little bit further south, but it seems plausible that you could have a more northern eruption that was blowing ash into this northern part of the basin where the Mercer is. So again, I talked about these two sources. I think we're converging on the idea that those evidence for volcanism is a little bit stronger based on other lines of evidence. Mercury values seem to be more aligned with volcanic source. There's various types of amorphous silicate minerals in the sample that seem consistent with the weathering of volcanic glass. Some of the isotopes may shed some light on this. So we're leading. There's still some debate, but I think we're leaning towards volcanism as the delivery mechanism for lithium-rich material into the basin. So with that, I'm going to hand it back to Tim, and he is going to
We'll do another tag team after this still. Okay. I've been advocating for a little bit more forceful statement from Nick, but he's not as encouraged as I am. You didn't mention immogolite.
Oh.
So we've identified immogolite in these samples, which is a clay mineral that's derived from volcanic ash. And Michael Cobal, the undergrad working on his senior thesis, has identified, is working on mercury content in these clay stones. And he's working on two sites, both of which have 700 and greater than 800 parts per billion mercury. And looking in the literature, volcanic ashes with mercury, 250 parts per billion is considered pretty high. So we may have some of the highest mercury values in these clay stones on the planet, maybe. Anyway, so we dug in a little deeper. So far, what Nick has presented to you is mostly from the Earth MRI data set. And so now I'm going to dig in a little bit more. We have an array of sites, 10 outcrops, 4 cores, all mostly from the Pennsylvania survey, but some from those local coal companies, ranging from, like I said, the northern central fields all down here along the Allegheny front part of the main bituminous field. You can see here an image from one of our northern center county sites, sandstone overlying an interval of shale and coal, overlying these historically mined for refractory clays, Mercer clay stones. And while there are variations to that basic stratigraphy, if you can remember sandstone, coal, claystone, in that order from top to bottom, that's basically what the Mercer is regionally. Key observations that we make in the claystone portions of these deposits. There are 3 things that are important that you can observe in the field, or down below here you can see in the microscope in thin sections. And these 3 things are paleosol slicken sides or slicken lines, roots, and siderite spherules. And each one of these has characteristics that help us to understand not only what this deposit is, but how it evolved. And in particular, I want to point out, I mean, the roots, what they tell us is there were plants living here on this stuff. These slicken sides, in modern soils, people might call them cutans. These tell us that clay material from high up in the ancient soil was translocated, or think percolated down with flowing water to deeper in the soil horizon. And as it flowed along macropores and areas of where water would concentrate, it got clay concentrated along those surfaces. And this happens today in a mostly monsoonal climate. And the key to those things forming is wetting and drying. So most of the season, the soil is actually quite dry. And then it gets a whole dump of rain on it, moves clay down in it, swells them up, and then they shrink. And then seasonally, every year, shrink, swell, shrink, swell, shrink. And that's what forms those shiny surfaces you're seeing over here. The siderite spherules form under totally saturated and reducing conditions beneath the water table. So seeing them also tells us something about the hydrologic conditions, the soil water conditions in these ancient deposits. Now, I'm going to look, so I didn't mention that the thickness of the Mercer throughout this region is somewhere between about, half a meter to more like 2.5 to 5 meters in thickness. And everywhere we look at it, we're sampling this in 20 centimeter intervals. And so the data I'm going to start showing you next, I'm going to begin with samples, just plotting all the information in a couple plots. So first here you can see aluminum oxides versus silica. And you see a relationship that shows the highest silica values correspond to the lowest alumina, and vice versa, highest alumina, lower silica. And what you're seeing here, for the most part, these down here are the coals. But for the most part, what we're seeing is the high alumina, low silica are the clays. There's very little quartz or silt quartz grains here. Whereas down here, this is the sandstones. These are the sandy intervals or silty intervals within the units. And if we plot these two over here versus lithium, what you can see is that all the high lithium values occur within the lowest silica and highest alumina-bearing samples. And so at least at a first order, what that suggests to us is that the lithium exists in clay minerals. Now, if we dig in here a little deeper and look at a plot of chemical index of alteration, which is defined up here if you want to read it, but basically it's a measure of weathering intensity, how deeply and intensively a mineral has been weathered in a soil profile. High numbers, intensive weathering, lower numbers, not so much. And it's a little scattershot, but you can manage to plot a line through it and generally see that the most intensively weathered intervals, the highest chemical index of alteration, have higher lithium content. And then similar to what I showed you in the last slide, higher aluminum, higher lithium. So not only do we see the lithium associated with clays, but we think it's also the most intensively weathered horizons within these clays. On this plot, I'm comparing that chemical index of alteration to loss on ignition, and using loss on ignition as a little bit of a rough, but as a proxy for organic matter. And here you can see the higher LOI values, higher organic matter content, are associated with those most intensively weathered horizons. In other words, the most intensively weathered horizons in these ancient soils contained a lot of roots. Those roots were probably part of the weathering story, right? It's their presence that led to or at least in part, led to the intensive weathering. In the interest of time, I'm going to skip the rare earth element stuff and go on to lithium. So what I've done here is picked 4 of our 14 sites that represent what we see internal to these claystone intervals, the internal stratigraphy or chemostratigraphy. And a couple things I want to point out is that first, coal everywhere. I haven't bothered to draw the sandstone on top. Immediately below the coal are the highest lithium values. Now, as Nick pointed out, we have a geographic distribution in high lithium. So here, Curwensville, Morgan Run's up near Phillipsburg. So up in, just north of us here are those hot spots that he referred to earlier on his map. As we go south down towards Johnstown and Westmoreland County, what we see is there's still elevated lithium beneath the coal, but it decreases the further we get from that hotspot region. A couple other points to make. In all of these sites, there are soil slicken lines. Some better developed in places than others, particularly here in Johnstown, where we get a fair bit of laminated sediment within the base of the paleosol. In all places, there are roots, and in all places deeper in the subsurface are siderite spherules. Remember, that tell us where the water table was and that it was reducing conditions at that time when the siderite formed. So we use all those observations to put forward the following model. Now, first of all, lithium-bearing minerals from whatever source were deposited on this ancient floodplain that Nick described earlier. The verdict is out, in my mind, as to where those lithium-bearing minerals came from. He presented 2 models, volcanic ash or detritus from the eroding mountains and the pegmatites in the mountains. I personally think, and I think I'm slowly convincing him otherwise, that the observations of amogolite and what we think are probably diagenetic results of weathering amogolite coming from volcanic ash, combined with the very high mercury values that we see, tell us that clearly there was volcanic ash deposited on this floodplain, and I think it was what was bearing the lithium. And hopefully his mineralogy will convince you of that. Um, these floodplains were intensive, went through an episode early on of weathering and leaching under relatively well-drained conditions. That's what those soil slicken lines tell us. Water was pouring through this out the bottom or down to a deep groundwater. But it was well drained and pouring through that. And it's under those conditions that a lot of the cations were stripped out of the soil and why we see those high chemical index of alteration values. Um, Lithium, being reactive and soluble, was oxidized and released during this time. And at least the way I think of it is that during this time, there was in these pretty low permeability floodplain soils, a deep, stagnant, shallow groundwater, relatively shallow groundwater flow system that could have served as a reservoir for some of the lithium to accumulate. Now, shortly after that, and we can tell this looking at thin sections, the siderite spherules come after those slicken lines. The groundwater table began to rise. And studies today in Japanese wetlands, in paddies, rice paddies, have shown that, because they get siderite forming in the rice paddy soils, that when siderite forms, it excludes lithium. It excludes other things too, but one of the things it excludes is lithium, and it concentrates it in the soil matrix and the soil pore waters. So lithium was arriving in this shallow groundwater system, and then as it began to rise and become reduced, further concentrated by the formation of siderite spherules. And from there, and this is the part that is a little bit of arm waving, but has backing, in the literature, is that the lithium was hydraulically lifted and redistributed by the plants, by the roots that extended down through much of the soil column, and not incorporated into the organic matter of the plants, but instead drawn upward and then released back into the shallow layers of the soil horizons. From there, the lithium was absorbed into the clays. And I'll simply point out that an interesting site here is at Curwensville. You can see high lithium below the coal, but over here you see this little squiggly line that's only a couple hundred parts per million lithium below the coal. And at that site, there are no soil characteristics. It's well laminated. So it looks to us like it was probably a pond on this floodplain. Lithium accumulated in it, but didn't get moved around because there were no soils. There were no plants growing on it. And so very close to this site that is like what I described, there are low lithium values below the coal where there were no soil features observed. And then finally, the water table eventually rose above the land surface. That's what the coal, the regional coal, tells us. For that to have accumulated, the water surface was above the mineral soil. And above the coals is shale. So the water table continued to rise. Once the water table rose above the surface, any biolifting by the plants ceased. And that's why there's no lithium accumulating in the coals themselves. Okay, Nick, you're up for the end of the talk.
So with that in mind, as a coda for while we're wrapping up, I want to just touch briefly on where the lithium actually resides. Can we shed any light on what the host of lithium is in these samples? In light of all of what we talked about of environments, various pedogenic processes, but can we say anything about where the lithium is physically? And so, as Tim mentioned, the highest lithium samples are the ones that are unusually enriched in aluminum and somewhat depleted in silica, but still have a fair amount of silicon. This is consistent with clays or aluminum phyllosilicates. These clay minerals, if you look at them under a very powerful microscope, you see that they're these flat, flaky things, and various chemicals and elements can stick to the surfaces. They're a little bit sticky. And so one question is, can lithium stick onto these crystal faces or adsorb onto the crystal faces? And long story short, that doesn't seem to be the case here. It can, yes, but that doesn't seem to be the predominant case here. We've done various leaching experiments, and through using different types of acids, certain acids will release the lithium that's absorbed. Yeah. And certain acids will release adsorbed lithium, and I've got various samples over here, and for each one of those samples, there's 3 data points. The amount of lithium released by nitric acid, which will release adsorbed particles, the amount of lithium released in carbonate, and the amount of lithium that will be released if you dissolve silicate, the silicate crystal itself. And this is a log scale, and it's not even close. It's structurally bound in the silicate itself. And so this was done as part of some ongoing lithium isotope work that Liz Andrews has done. So thanks, Liz, for this great data. And so when we talk about aluminum phyllosilicates, there's sort of 3 main candidates. Based on our own mineral work and previous work, there's sort of 3 big groups. And these are composed of distinct layers, like these are layered crystals. That's one thing they have in common. There's layers of these little tetrahedra and octahedra stacked on top of each other. But a couple things to bear in mind. For the kaolinite, it's almost entirely aluminum, silicon, and oxygen and hydrogen. So almost like it should be pretty close to pure aluminum silica. For illite and mica group minerals like muscovite, you would expect a little bit more magnesium and iron, but also the key thing is potassium. Chlorite is another potential candidate, and chlorite should have less potassium, although plausibly have some. But the key thing is more magnesium and iron. And so we're trying to explore all of these 3 things have been found in the Mercer, and we're trying to disentangle where the lithium actually resides. And if it's in the crystal structure, it's associated with these crystal lattices. Most likely, the element that lithium most readily substitutes for is magnesium. So the magnesium things like right here, magnesium right here, and these are the octahedral layers. So that's where I would suspect you would find the lithium. So what can we do to resolve where it is? And so we've been throwing a bunch of different tools and techniques at it. This is a scanning electron microscope image of a sample of the Mercer clay with elevated lithium. And what we can do is apply this mineral mapping technique to it. And so it goes through through electron dispersal spectroscopy, you can get a sense of the chemistry at each point along a 10 by 10 micron pixel size on this sample. And so this is a mineral map superimposed on top of the SEM image. The pink here is quartz. There's a little bit of red titanium oxide, but all this green stuff in here is the clay. Now, the downside of this mineral mapping technology is that it can't actually see lithium itself. So what you might notice is that there's this little black line through here. These are actually pits from a laser that blasted off a little bit of sample, and then analyzed the ejecta and through a technique called laser ablation inductively coupled plasma mass spectrometry, which can detect lithium. And so what I've done is I've superimposed the lithium values for each one of these little pits that was taken across this transect. And you can see it's in the green area. And the greens are mapped as kaolinite, illite, chlorite, muscovite. So it's kind of all those things. So taking a deeper dive, this is a closer look. According to the mineral mapper and according to other independent lines of mineralogy, the samples seem to be predominantly kaolinite, but it's complex. There's little brown pixels in there, darker green, lighter green, more yellow green. So it doesn't seem to be just a pure kaolinite ground map or kaolinite matrix. It seems complex. And so we can look at the laser ablation data through here for all these different elements. And what we can see is that the lithium seems to covary with all of them: aluminum, iron, magnesium, and most notably potassium. And so unpacking that a little bit, so in here, instead of plotting the laser ablation data as a function of space along the slide, I've just done a cross plot of the lithium values plotted against the potassium values. So each one of these is like a single data point that gets you potassium and lithium values, and we're plotting them together. And these are four different samples, four different transects on different samples. And for each one, I've color-coded them differently. And for each one, I've also put superimposed here the bulk lithium concentration of the sample as a whole. And so the low lithium sample has low lithium also in the LA-ICP-MS. But what we see is as you go to higher and higher and higher lithium values, there's basically the curve gets steeper and steeper and steeper. And what this means is that in these samples, the lithium is covariing with potassium. But overall, as you go from low lithium to high lithium, the overall potassium in the sample decreases. But I think the important thing is that there is this connection between the lithium and the potassium. And sort of the traditional view would be that this covariation seems to point, the fact that the lithium and the potassium are being found together, I think points more towards illite or muscovite being the principal host of the lithium in these samples. Although, we can't quite rule out chlorite. Like, chlorite can have some potassium, but I think overall, this suggests that the illite is most likely the primary lithium host. But as I said, it's more complicated than that. It's more complicated than that. So on this final note, just one last thing. It's not just looking for illite mica or muscovite. And muscovite and illite are kind of very chemically similar. Just it's a matter of crystallinity, essentially, like how well developed the crystal is. But basically, so on the left here, we've got a sample with low lithium, and on the right, we've got a sample with higher lithium. And on each one, I've plotted the LA-ICP-MS, the lithium abundance, as this purple line. And the low lithium sample has a lot of mica and a lot of illite, a lot of muscovite, the brown in here, and a lot of clay, like illite. But what I noticed is that the clay, the greens, and the browns are sort of these, it's very partitioned. There's blocks of green and blocks of brown and blocks of other things. In the high lithium sample, it's all much more heterogeneous and mixed together. And it's like this very kind of messy mosaic. And as this intermediate step, this is a sample between these two samples with intermediate lithium. And the lithium is still concentrated in the clay, the green stuff overall. But there's one distinct peak in the lithium values at this intermediate section, at this intermediate sample that's comparable to the high lithium values. And at that site, that's where the laser transect crosses over this zone with a lot of brown pixels in it. And so brown being the muscovite. So the texture I was seeing here with this lithium spike it just looked more like this high lithium stuff in here. So what I think this means is that some kind of fine-grained illite or muscovite type mineral is the predominant lithium host, but it's complex, it's fine-grained, and it's very much intermingled with lots of other clay phases like kaolinite and chlorite in there as well. But it seems that some kind of fine-grained muscovite or illite-like mineral is the key host of the lithium. We're still disentangling this, but this is kind of where this has been leading us as we're diving into this data. So to wrap that all up, through the synthesis of data, we've identified these lithium hotspots. We've placed them in an environmental context. We think that it's, again, probably a volcanogenic source related to pegmatite emplacement in the Appalachian Mountains, but it's not just that. There's a distinct suite of having it, you have to have a distinct I don't know, Goldilocks zone of the right environment and the right environmental processes and the right types of pedogenic processes, like the right kind of soil conditions, all converging on the right parameters to create these lithium enriched clays in just a few regions in the northern Appalachian Basin. And so some ongoing work is we're doing some ongoing mineral work and looking into lithium isotopes with Liz and Michael's mercury work. And also, incorporating some of these results into a more economic assessment of, is this really plausible and is this really economic? And trying to get some of these results out there. So with that, we'll take any questions.
I was kind of anticipating it would be in the because I would have thought lithium as a monovalent cation might be fixed in the inner layer of those clays, and then and then would be held in the lattice and not exchangeable if if it starts out as a smectite, volcanic smectite, and then it is illitized and the lithium's fixed in the inner layer. So because it sounds like you're focusing on the octahedral layer position, but is lithium not found in the inner layers of the line?
That's something I need to dig into more. My general impression from the literature is that the difference in like the atomic radius between lithium and stuff like potassium is too substantial that lithium doesn't readily substitute for it and behave chemically similar to it. That's the general impression I have, but it's something I should definitely look into some more. Yeah.
First of all, very good talk and very nice presentation, good research. So I was going to say some may recall that Blaine Cecil from the USGS and Jim Cobb from the Kentucky Geological Survey performed a study some years ago comparing the coal basins in the Appalachians with those in Sumatra, showing that they're both likely domed deposits, and that they were formed in kind of ever wet conditions that might be similar to the siderite occurrences that you see in the Appalachian area of the Mercer. And of course, Sumatra is largely a volcanic back arc basin, and it does have significant lithium deposits. And I wonder if there's any interest in the analog between the lithium in the Appalachians and the coal basins there and those lithium deposits associated with the coal in Sumatra. And even the Topo High 4 bulge in the Appalachians may have some analog with the doming of the coal basins in Sumatra. Just an idea for an analog potentially.
Yeah, we're interested now. Most of the analogs I've come across personally, there's a lot of apparently very similar types of aluminum-rich carbon, coal sequence rocks in China that are also high lithium, that are also coincidentally, or maybe not coincidentally, Pennsylvanian in age, or Permian, yeah. I think some are Pennsylvanian, but yeah, but we'll definitely do some digging on that.
Okay. Good talk. Thank you.
I'm looking at Patrick's question about magnesium substituting for aluminum charge imbalance. I've also read something similar that's seemed more plausible to me for the Mercer was that the Mercer is quite depleted in silicon specifically, with the idea that the silicon, which is this +4 ion, getting swapped out for aluminum. And so there's a charge imbalance there that potentially lithium accounts for. I've read people making that argument in other rocks. Yeah, I think this definitely seems plausible as like so some of these like silicon depleted or aluminum depleted rocks somehow like that depletion is priming them as a lithium sink. That's something I've given thought to, and it's appealed to me. But yeah, we just need to do a little bit more digging on that.